Okay, we are on to chapter 13, which is equilibrium. And this really is the sort of main topic of the course. Like I said before, we're going to talk about all kinds of equilibrium. As we talked about last time, equilibrium is for a certain type of reaction, which is a reversible reaction, arrows heading in both directions. And as we talked about, was considered the forward direction, which is our reactants going to our product. At some point, we will build up enough products that they will actually start to combine and actually send the reaction in the opposite direction, which is referred to as the reverse reaction. And at some point, it will reach chemical equilibrium. And as we talked about, what chemical equilibrium is, again, is it does not mean that you have equal amounts of stuff on both sides of the arrow. It's actually referring to sort of the rate and the kinetics of the reaction. So that means that the rate of the forward direction will equal the rate of the reverse direction. And ultimately, the sort of consequence of the rates being equal to each other going forward and reverse is essentially it will lock everybody into place in terms of their concentrations, or if you're looking at pressures in terms of their pressures, when it does reach equilibrium. So they will be able to kind of maintain their concentrations because, again, as soon as it kind of goes one way, forward direction, it's just going to shoot back the other way about equal rates. So it's going to be a net tie and nothing's really going to change unless you do something to screw up the equilibrium. Now, one of the relationships that we use with equilibrium is the equilibrium constant. And the equilibrium constant is written, or the expression is written from the actual balanced equation. So this would be Kc, which would be the concentration of C to the C, D to our D, A to the A, and B to the B. So unlike kinetics, we actually do use, when we write an equilibrium constant expression, the coefficients as the exponents. It's also capital K as well. Kc here stands for concentration, and that obviously is an equilibrium constant that deals with concentration, and that is what that brackets mean, right? It means basically molarity in most cases, moles per liter. And essentially what we're doing is we're taking our products divided by our reactants. So one of the things that we could kind of gain knowledge from in terms of the equilibrium constant value is what is going on in this reaction when it reaches equilibrium. So if you have a K value that's considered large, what that means is when you reach equilibrium, you should mainly expect to have products. And vice versa, if you have a K value that is small, that means you would mainly have reactants present when you reach equilibrium. And it's just a math sort of thing, right? Obviously, if you have a large number on top divided by a small number, that's going to give you a large number. And again, that means you'll mainly have products. Vice versa, if you have a larger number on the bottom and up on top you have a smaller number, that's going to give you a smaller number for the equilibrium constant value. The equilibrium constant value is actually just a number. Thank you. It has no units associated with it. So, and really it's because the units usually don't cancel out perfectly and stuff like that. So we usually do not use units with it. Remember that what we consider sort of a large value of K is 1. So anything above 1 is considered large. Anything less than 1 is considered small. And there are some extremes, as we talked about. Again, you could have really, really large K values, and you can have really, really, really small K values, and you can really have K values anywhere in between. So there are some, as we talked about last time, that are so large that even though it is sort of a reversible reaction, it's essentially just kind of going to the product side in a one-way street. And vice versa, you have things that are so small that even though it's basically saying in the reactant side, nothing much is going to the product side. But even at those extremes, as we talked about, it is still a reversible reaction. So you'll still have just a little bit, not very much, going back and forth on each side. Now, we also talked about the idea that the only thing that can affect the K value is actually temperature. And Temperature will change the value of the equilibrium constant when you're comparing between two different temperatures for the same reaction. We also talked about that if you keep it at the same temperature, it does not matter, what you start with. Again, you can start with all reactants, start with all products, you start with a little bit of everybody in the pool swimming around, and it will eventually come to the same ratio, right, of products to reactants, and you'll get the same equilibrium constant, regardless of really the amounts that you start with, as long as you don't change the temperature. So if you did, like we talked about last time, 4 different experiments where you started with different amounts in each one, as long as the temperature again remains constant, you should end up with the same ratio of products to reactants. It's only when we do change the temperature that you will see a different equilibrium constant value, and it will be determined, whether it goes up or down by sort of what's happening. But again, if you change the temperature, say from 25 degrees to 40 degrees, and you did another 4 experiments at 40 degrees, all 4 of those should again be the same. But in comparison to 25 to 40 temperature K values, those guys should be different. Any questions on that stuff we talked about last time? Okay. And then, so that's what we got into again last time. Our value of K does give us some good information sometimes, and it's actually important in terms of the calculations that we do here in this chapter and later chapters as well. Sometimes the value of K will help you determine which way you might want to approach the calculation that's involved, whether it's a really large value or a really small value. It can have, again, an effect on maybe the way you want to kind of approach a calculation. All right, so if we take a look at this here, we have Mickey at the start of the day reacting with a couple of those things, and then after a long day, Mickey needs a nap upside down. K value here is 25. Would we expect that equilibrium reactants or products in this case? Which way? We should expect products, yeah. So K of 25 is considered a large value, which means that we should expect products here to be formed here in this reaction. So homogeneous equilibrium applies to reactions in the same phase, basically. But we can write, obviously, for this reaction, our equilibrium constant, our Kc value here, which is our NO2 squared because of the coefficient, divided by N2O4. And again, the coefficient here is 1, and we don't really need to put the 1. But in this particular case, everybody is gases here. And when we think about gases, sometimes we may not want to look at concentration, but we may want to look at pressure. So you can do an equilibrium expression that deals with pressure. It works the same way. You're still going to take your products over your reactants. And the only difference is you're going to take the partial pressure here. So the partial pressure, we will still square it because of the coefficient of NO2 divided by the partial pressure of N2O4 in this case. This is what is sometimes referred to as a Kp value. I'm going to go with pressure for P on that one there and C for concentration. So we could write 2 expressions for this. Obviously, you need some gases involved in order to write a Kp expression. If you don't have gases, then you probably don't have pressure, so you can't really write one. So you do need to have some pressures involved. Now, when we talk about pressure and we talk about doing calculations, which you absolutely can do as you go through equilibrium in pressure sort of calculations, the standard unit of pressure usually is atmospheres, and atmospheres again is usually the unit, especially later on in the chapter when we start doing real sort of equilibrium calculations. You usually want to make sure that your calculation is done in atmospheres and not some other unit like millimeters of mercury or torr or something like that. A reminder, right? 1 atmosphere is 760 torr, right? And like 760 millimeters of mercury, right? So sometimes later on when there's some calculations you have to do, sometimes people miss them because in the problem, they will give you the pressure like in torr or millimeters of mercury, and they'll ask for the answer in torr millimeters of mercury. But actually, when you do sort of the equilibrium calculation, you actually have to convert them to atmospheres, do the calculation, then convert them out of those units. So just keep an eye on that a little bit later on. Sometimes that does pop up. Now, typically speaking, the Kc does not equal the Kp. It is possible that they can equal each other, but in a lot of cases they do not. So there is sort of a relationship between those two, and the relationship is the Kp value equals the Kc value times RT delta N. R is our gas constant from like the ideal gas law, 0.08206 liters atmosphere Kelvin mole. Or if you learn the more rounded number of 0.0821, same thing. T is our temperature, and much like our gas laws and all those things, it does need to be in Kelvin. And delta N is actually the change in the moles of gas. So just the gas ones there, the change in the moles of gas. And you do want to take products minus reactants. So for example, say I have 2A goes to B here. My delta N in this case is what? It is products, which is 1, right? It's coefficient. That's a gas minus our reactants, which is coefficient there, and that is -1, right? Now, if you just take the difference, it's 1. Is there a difference when I go into this part of that equation for delta N if I put 1 or -1? Do I get a different answer? I do, right? -1 is like 1 over it, right? It's reciprocal. So you want to be really careful here and not just take the difference of the gas molecules, because if it is negative, it will obviously affect the calculation part. So sometimes people just kind of take the difference and don't worry about the negative. Here you do have to make sure, obviously, you worry about the negative if there is a negative. If there's not, obviously, you keep it positive. So why would you need this equation? Well, you may have a problem where maybe they give you all concentrations, but you were looking for like the Kp value, right? So clearly you have no pressure information or anything like that. So if you're given all concentrations, you could calculate the Kc and then use this equation really to get you to the Kp, and vice versa. If you're given a problem where maybe you're given all pressures, but you want like the Kc value, you again could get the Kp value, use this equation, and convert it into what you're looking for, the Kc. So again, that is the way we could kind of do that. Now, in a homogeneous mixture, there are a couple of things that do occur. And if we look at this reaction here and we were to just write the equilibrium constant expression, like we've been talking about, where we take products over reactants, we would take the acetate times the hydronium divided by the acetic acid and the water. Now, water here, though, is a pure liquid. And typically speaking, pure liquids in the reaction, their concentration is so large, it pretty much remains constant. So we do not include anything that is a pure liquid in the equilibrium expression. So for this reaction here, this would be the correct equilibrium expression where we would not include the water that's in the liquid state, or really any liquid. In general, we'll kind of jump a few slides here, but in general, we do not include in the equilibrium expression anything that's a liquid or a solid. So anything that is a liquid or a solid is not included in the equilibrium expression. That pretty much leaves you two things that are included, and the things that are included in the equilibrium expression are things that are aqueous, because basically they're floating around ready to react, and things that are gases, because frankly they're flying around and they're ready to react. So if you think about a solid, it's just kind of sitting there doing not much unless you dissolved it, then it would no longer be a solid. So it's just kind of hanging out. And again, liquids typically have pretty high concentrations, which remains constant throughout the reaction. So those two things are not included, liquids or solids. Aqueous and gases are included. As we talked about as well, again here, no units associated with the equilibrium expression are constant. We just basically have a number. Any questions on that? All right, so why don't you do it? Write the Kc and Kp for each of these, if possible, the Kp. Okay, let's take a look. So on the first one here, we could write go this way. Our Kc, again, it's going to be products over reactants. So here we would take the NO2, and again, we would need to take it to the fourth power because of the coefficient. We're going to times it by the O2. Obviously, the coefficient here is 1, so we don't need to put it. It's implied, divided by our reactants now, N2O5. Once again, we do need to square it because of the coefficient. And that's all that's there. So that would be it right there. In this case, we definitely have gases, so we can write a Kp expression. It's pretty much identical to this, except again, we're using partial pressures. So this would be the partial pressure to the fourth power of NO2. Again, do have to take coefficients into account, times the partial pressure of O2 divided by partial pressure squared of N2O5. Questions on either of those expressions there? Yeah. What does the P represent? Pressure. Yeah. You mean this P? Is that what you're asking? Oh, these P's? Yeah, they represent the partial pressure of each of those. Yeah. So they would be pressure sort of values like atmospheres and stuff like that. Yeah, that you put in there. Other questions? All right, looking at the second one, we could write our Kc here, which would be, again, our products, which would be our H3O plus concentration times our F minus concentration divided by our HF concentration. Am I putting water in this one? I am not. Again, it's a pure liquid, so again, we leave it out. By the way, if water was a gas and the steam, would I include it? I would, yeah. Again, because it's in the gas phase, it's moving around, it's participating and stuff like that. So um, sometimes people think all water versions are excluded. It's really just most commonly you come across the liquid version of it, and that's the one obviously that gets excluded. Can we do a KP for the bottom one? We cannot. There's really no pressures, so we can't really do no pressures. There's no gases, so there's no pressures associated with it. Any questions on how to write the expression there? All right, so why don't we try one here, a little calculation. The equilibrium concentrations for the reaction between carbon monoxide and molecular chlorine at 74 RCO is 0.012 molar, chlorine is 0.054 molar, and CoCl2 is 0.14. What is the Kc and Kp values? All right, so take a few moments. We're going to calculate those. Actually, a calculator would be good. I can try and find mine. All right, let's take a look. So clearly in this case, we're looking for both the Kc and the Kp value, and we are given concentrations, so it would probably make sense to attack the Kc first, right? Since we have the concentration given to us. Clearly, if you go into either a Kc or a Kp or really any equilibrium expression, obviously it needs to be equilibrium concentrations and not initial concentrations, right? So in this case, we can assume we got equilibrium concentrations here. We're going to do our Kc expression, which again is our products, which in this case is CoCl2, divided by our reactants, which is Co and Cl2. Again, we're just going to put in our numbers in the right spot here, which would be 0.14 divided by our CO there of 0.012 and 0.054 there, right? So if we slap all that into our calculator carefully here, 0.14 divided by 0.012, 0.054, get about 216 on that. Heck, if you're still looking at sig figs at this point, maybe a 220, right? If you got that going on there. That would be our Kc value in this case. Now, we can now get to our Kp using that formula that we saw there. So to go from our Kc to our Kp is equal to our Kc RT delta N. So we do need to do a couple of things here. Obviously, our temperature here was given to us in Celsius. So we need to do a little conversion there, a little 273 action there, which should convert that into Kelvin. And that's going to get us a 347 Kelvin. We also need to figure out our delta N. So our delta N in this case, again, is the moles of our products minus the moles of our reactants. So on our product side there, we got 1 mole. On our reactant side, 1 mole there and 1 mole there. Again, you can just add the coefficients of anybody that is a gas. So that's going to be the -1 here. And again, as we talked about, we definitely want to do products minus reactants. As you can see here, it gives us a -1, which is important for when we do this calculation. So that's everything we need here. So we could go Kp is equal here, I guess 220 we'll go with, why not? 0.08206 or 21 or 347 and a -1, right? So we'll clean up what's on the inside there, 0.08206 times 347. We're then going to take it to the -1, and that'll get us essentially 220 times 0.0351187-ish. We're going to multiply that by 220 or 216, gives us 7.7 as our Kp value. If you use the 216, you got 7.6, I think. Yeah, so pretty close as well. First off, any question on the calculation here? Yeah. I went to 220 just for normal sig fig wise here. Everybody's 2 sig figs, and we're multiplying and dividing basically. So you look at the smallest number of significant figures. Yeah. And second sig fig would be here. We have to round because that's a 6, right? And that takes us 220. Other questions? So what we see here first off is this K value is small or large. The Kc is large. And how about the Kp? It is also large, yeah. So that should agree with each other, right? So if you have a large Kc, you probably should have a larger Kp as well. Obviously, they're not the same value, which is very common. Again, they can be in certain cases, but they should tell you the same thing. So just like with the Kc value, if you have a large Kp value, it tells you mainly have products, which means if you mainly have products, you probably mainly have a lot more concentration of products than reactants. That's causing the pressure in this case. All right, let's take a look at another one here. The equilibrium constant Kp for the reaction at what is 158. What is the equilibrium pressure of the O2 if those look the same? I want to go with, maybe I'll go with that one. We'll go with that one as NO2. We'll go with the partial pressure of NO2 is 0.4. Partial pressure of NO is 0.27 atmospheres. We're looking for what is the equilibrium pressure of O2. So take a few moments here, and we're looking for a pressure, and we have the Kp value. So we'll start with the Kp expression, which is the partial pressure here squared of our NO, which is our products, and our partial pressure of our O2, divided by our partial pressure squared, again for the coefficient of our NO2, and that's going to equal 158. So we can put in our numbers that we have. So we do have NO, which is, we went with 0.27. Again, we do need to square it, times the partial pressure of O2, divided by our NO2, which was 0.4 that needs to be squared, equals 158. We're going to multiply that to the other side, and then come back and divide that over there to the other side. So we'll take 158 times 0.4 squared. And if you do that, I'll write the answer here. Looks like we end up with this here, 25.28. We're then going to divide that there. And if we divide that there and maybe punch in the right number would be helpful. Let's try that there. There we go. Looks like we end up with a partial pressure of O2 of about 347 atmospheres in this case, yeah. Which I would definitely say is a pretty high pressure, yes, in this case, yeah. It also does make sense, right? Because we have a fairly high equilibrium constant of 158, right? So that means that we should head towards the product side, which means we probably have a lot of products, and O2 is on the product side, so that's good in that sense. Yeah. Any questions on that calculation there? All right, let's see what we got going on here. So heterogeneous equilibrium is when we have everybody not in the same phase, and we sort of jumped on this a little bit earlier. But the other thing that we typically, again, do not include in the equilibrium are solids. And in this case, we have actually two solids here. So again, if we wrote our equilibrium expression like normal products over reactants, in this case, we would actually want to get rid of the two solids. And that would leave us a Kc expression for this, which is really just the CO2, and a Kp expression, which is the partial pressure there of CO2. Now, what would happen, for example, if you had something like this, maybe aqueous goes to solid, right? So let's just say we have something like this where we have something on the product side that we really would not include in the equilibrium expression. To write the equilibrium constant for that, we would actually just take 1 over what's on the reactant side. So if by some chance you come across an equation where everything on the product side should not be included, you just basically do 1 on top there for the products and then over whatever needs to be included there on the reactant side. So as we talked about earlier, solids, pure liquids are not included in the equilibrium expression. And again, in this case, we could write two equilibrium expressions for it, RKP and RKC. Again, we could write the KP in this case because we do have obviously a gas involved in this case. Yeah.
The solids, but the reactants don't work. The reactants are, we usually would do the 1 over, but if it was the other way around,
The products, like in this example here. In this example, we're actually not using any of the reactants, right? So basically, the equilibrium constant is just the products. And as you correctly said there, if you had solid or even liquid, and those were whatever things you had on the product side, you would just do 1 over the reactants, whatever be included. Yep. Other questions? All right. So again, as you can see, solids really not participating. Uh, the only way they could really sort of participate, for example, is if you dissolve them. At that point, they would no longer be solid. They would be aqueous, which means they would be participating at that point, or evaporate into a gas, which again, at that point, they would be in the gas phase and participating. All right. All right, let's try one more here. Consider the following equilibrium at 295. The partial pressures of each gas present is 0.265 atmospheres. What is the Kp and Kc for this one? So give it a go. Search given pressures. So again, it would make sense, obviously, to start with the Kp. So we'll start with the expression here. My Kp would be the partial pressure of NH3 times the partial pressure of H2S. And in this case, this is a solid, which means we would not include it into our expression. Each of our gases has the same pressure, so that's going to basically give us 0.265 times 0.265. And that will get us here for our Kp. Uh, 0.265, right? I hit the right button. 0.265, there we go. 0.0702 as our Kp value. Again, we can use the formula we saw earlier to go from Kp in this case to Kc. Kp will equal our Kc RT delta N. So our temperature here is already in Kelvin, so we're good on that. Our delta N in this case will be 1 gas molecule, 2 gas molecules on the product side, minus obviously 0 as that is a solid. So our N in this case would be 2. And I think that's all we need. So we'll go 0.0702 equals Kc. Again, the gas constant there, 0.08206 times our temperature, 295. And again, that's going to be squared. So if I clean up the right-hand side there, it looks like we are at about 0.0702 equals Kc, 586.0127. Gonna then divide that to the other side, and 0.0702. Where did that number go? I'll just use the whole number there. Divided by 586.0127. Gonna get us here a Kc of about 1.20 times 10 to the -4, I believe, in this case. Yeah. Question on that calculation there. Now, again, we see here Kp value is a small value, and so is our Kc value as well, small value as well. So they're both relatively small. Any questions on that there? All right, so let's see. Let's talk a little bit about what happens when we sort of manipulate equilibrium equations and what happens with sort of the K value when you do so. Now, as you know, and as we talked about, not all reactions do occur in a one-step sort of process. So sometimes they are, again, a result of multiple steps sort of added together. So if we were to add two equilibrium reactions together, just like kind of normal here, we would cancel out anything that's on opposite sides of the arrows and leave everybody on the left-hand side on the left-hand side at the end of that, and on the right-hand side on the right-hand side. And if we're looking for what the equilibrium constant is for our new sort of equation that we built, we would essentially do, again, our products over our reactants here, E times F divided by A times B. So what does that mean for these two? What that means for these two is we're actually multiplying those two values together. If I multiply both of those expressions together, those cancel out, and it leaves us our equilibrium constant for the overall reaction. So if you have multiple equations that you're going to add together, the way you do it with the equilibrium constant value is you need to multiply the equilibrium constant value by each other, not add. So that's a common error that people make because in their head at this point, they still think about like delta H and you just add up all the delta H values when you do that. Here, though, with equilibrium, it is different. You do have to multiply each of the K values together to get the overall K value. Any question on that there? Now, there's some other ways that we can manipulate an equation and the effect on the K value. Let's say we take a look at these two reactions here, our equations, and on the left-hand side, that's N2O4 going to 2NO2. On the right-hand side, this is the reverse of the first reaction. It's 2NO2 going to N2O4. What happens when you reverse a reaction is your reactants become your products and your products become your reactants. And what happens in the case of the equilibrium constant is you would have to take 1 over the equilibrium constant. So if you reverse a reaction, you actually would need to take 1 over the K value that was given to get the new K value for that. And in this example, it would be 216 by taking 1 over it. Again, also a very common error people do with this is that they do like they do in delta H, they just like put a negative or change the sign. You don't do that with equilibrium constants. So you gotta take 1 over it. By the way, when you do see an equilibrium constant that is written, it is written specifically for the equation as to who's the reactants and who's the products. So in this case, if I said my equilibrium constant was 4.63 times 10 to the minus 3, that would be specifically for my N2O4 as a reactant and this guy as my products. If I'm talking about this reaction here, that would be the K value for it. So when you do see the K values, it's specific for how the reaction is written, who's the reactants, who's the products, and so forth. Any questions on that there? Now, what are some other things that you may do to these reactions? Let's just say we had a reaction such as this, right? Obviously, we could write our K here, which is our C, times our D divided by our A and our B. Now let's just say that we did not need, say, just one of A, but we needed like two of A. So we would have to take this equation and basically multiply everybody by 2, and that would get us 2A plus 2B goes to 2C plus 2D. And our K expression for this would be C squared D squared divided by A squared and B squared. So the difference between going from this equilibrium expression to this equilibrium expression is what happened to it? I basically squared it, yeah, and that's because I multiplied by 2. So if you have to multiply by a common number, you take k to that common number. So if you have to multiply by common number, you take k to that number. So that means, for example, if I multiplied by 3, I would cube the k value. If I multiply it by 4, I take it to the fourth power and so forth. So if you have to multiply an equation by a common number, you basically would take the k value that you had originally to that common number. What is the other thing that you could do? Obviously, the last thing that you could do is, let's say we started with this reaction. And obviously here, our k, like we see above there, is our c squared, d squared, a squared, and b squared. But let's just say in this case, if we started with this guy and we didn't need 2 of A, but we actually only needed 1 of A, we would need to go through and again, in this case, divide by 2 all the way across. And if we divide by 2 all the way across, that takes us down to A plus B goes to C plus D, which means our K in this case would be C, D, A, and B. So in comparing coming from here to here, we actually took the square root of it basically, yeah, and that's because we divided by 2, and we end up with that. So if you have to divide by a common number, you would take the k value to the root of that common number. So here I divided by 2, so I took the square root. If I divided by 3, I would take the cube root, the fourth root, and so forth, depending on what you divide by. So those are really the kind of the 4 ways that we sometimes will manipulate equilibrium reactions to kind of build the overall reaction that we may be interested in. Again, if you reverse an equilibrium reaction, the effect on the k values, you take 1 over it. If you add multiple equations together, you need to multiply the k values from each of those individual ones together. If you multiply by a common number, you need to take the k value to that common number. And if you divide by a common number, you need to take the root or square root, cube root, whatever root of the k value to whatever you divided by. Yeah. You would, in this case, if I understand your question correctly, for example, we would have this reaction given to us, and maybe it'll say, hey, the k is 20. And you would just, in this case, we divided it. So we would take the square root of 20, basically. And that would give us the overall the overall k value for this one. In that example, you would take the square root of 20, would be. Correct. So usually in probably this application, in most cases, what you would be given is like you'll be given individual sort of equations with different k values and stuff like that, and very similar to what you did with Hess's law, where you kind of have to manipulate each of the individual reactions. And as you manipulate them, you just want to keep track of it, and you would just either take that k value that was given to you for that first reaction, whatever you did to it, and either square it if you multiply by 2, square root it if you divided by 2, take 1 over it if you reversed it, and stuff like that. Yeah. So it's very similar to, like I said, like what you did with Hess's law, where you did that, but the way that you treat the k value is very different than how you treat the delta H value and stuff. So it's a very common thing. Like I said, people kind of get those two confused, and they just kind of roll back to like, okay, I reversed this, so I'm just going to change the sign, or I multiplied by 2, I'm going to multiply the k value by 2. So again, you got to make sure that you kind of do the adjustment correctly. Other questions? All right, why don't we try one here? So we're looking for the K value of the top equation based off of the two bottom ones there. So take a few moments there, rearrange it. Really, you want to keep it kind of simple as possible when you're doing these type of things, just like with Hess's law. Really just want to think about just getting everybody to the correct sides, right? And just kind of see what you need to do that. So for example here, if I look at the first equation here, I got A and B. That's on the left there, but it is on the right here. So I do know I need to reverse that one. So I'm just going to do that first. So we'll go 2C plus 2D goes to A plus B. Again, because I reversed it, remember here, we don't change the sign. It is 1 over the K value. Yeah, so I need to take 1 over the K value in this case. So now I could look at the other stuff here. I got E and F on the left and E and F are on the right. So I do need to reverse that to get it to the correct side. I also need not one E, but I need two, right? And also need two Fs. So not only do I reversed obviously the first one, I need to reverse the second one and I need to multiply by two, right? To get me everything that I'm going to need here in the end. So I'm going to first reverse it here. So that will take me to E plus F goes to C plus D. Again, by reversing it, I am going to take 1 over the K value. I also need to multiply it by 2, which means I will end up with 2, 2, 2, 2. Once again, we're not going to multiply the K by 2, but take it to obviously the power here. And that's going to give me my overall reaction that hopefully I did correctly here. Opposite sides should cancel. And that is not what I want to put a line through, I don't think. Try that again there. There we go. All right, let's try and put a line through the right stuff here. So obviously C and C will cancel, D and D will cancel. Everybody on the left-hand side stays there. 2E plus 2F goes to A plus B. So that looks like a winner here in terms of our overall reaction. I'm just going to call this K1 and K2. So my KC for this would be K1. Remember, we're not going to add, but multiply, right? The two K values in this case. So if we kind of individually here get some numbers, 1 divided by 100, 0.01. 1 divided by 20, and then square it. Gonna get us here 0.0025. Once again, we're going to multiply those guys here to get our overall K value, not add. And that's going to get us here a maybe 2.5 times 10 to the something there. 1, 2, 3, 4, 5, minus 5. Minus 5 in this case. Any questions on that? Yeah. Yeah, if you multiply, in this case, we multiply by 2. And that means we would need to square it. If you multiply by 3, you would need to cube it. Take it to the third power, multiply by 4, you need to take it to the fourth power and so forth. So by whatever number you multiply everybody by, you need to take the K value to that number. And same thing if you divide. So whatever you divided everybody by, you would take the root of that, either the square root, cubed root, fourth root, whatever it may be in that case. Yeah. Other questions? Let's try one more here, maybe to finish up. What is the K value of our overall reaction here based off of these guys? Okay, so since we're getting to the end here, let's take a look, see how you're doing. Again, just gonna kind of take a look at getting everybody on the correct side. So I see in my desired here, I got N2 on the left. I do have it on the left here, so I don't need to reverse this reaction, but I do need 2 of the N2. And in order to get 2 of the N2 with that coefficient, I actually need to multiply by 4 in this case. And if I multiply by 4, that will give me 2N2 plus 12 divided by 2 is 6H2, gives me 4NH3. Now, because I multiplied everything by 4, I am going to take the 411 to the fourth power. Again, based on what I multiplied by, will be where I get that from. On the bottom here, again, I need water on the left, and I do have it on the left, so we're good there. But we do need 6 waters, so I think we're gonna have to multiply the bottom here by 3, and that's gonna give us 6 waters. Goes to 6H2 and 3O2. Here I multiplied only by 3 in this case, so we're going to actually cube the K value. Now, if I did this correctly, we should end up with that equation. So we're going to add these together. The H2s should cancel, and I think that is it. So that will leave us 2N2 plus 6H2O goes to 4NH3 and 3O2. So it does look like we did good on the equation. Let's call that K1 and K2. So the Kc for this would be K1 once again times K2. So I'll come down here and do that. So that's going to give us 411 to the fourth power. Oops, wrong button. 411 to the fourth power. And I'll give it something like 2.853 times 10 to the 10. And we're going to times it by 0.345 to the third power, which will give us something like 0.041064. We'll multiply those two together. Gonna get us a big old number. I guess that's what happens when you make up numbers. Let's see. So you got 1 point. We'll go with 17 times 10 to the 9, I think, in this case. If I did not mess that up, hopefully. Any questions on that? So again, sometimes you do need to manipulate these equations. The key is just to keep track of what you did and make sure you adjust the k values. And again, don't adjust them like you would do with delta H because you'll get it wrong. And again, that's a very, very common error people make. Any questions